Hi, can you hear me? Yep. So I want to start with a probability question based on real-life events. I'm currently trying to apply to 2 different companies for a research internship, and each company independently has a probability of 3/4 of giving me an offer, so 1/4 of rejecting me. And I'm just curious to know what's the probability that I would not have a single internship offer. So each company is independent, and so the answer is 1/16. You multiply 1/4 by 1/4. And we can model this with a sequential stateful program as so. Here, I create a reference that points to 0, and I perform a biased coin flip with the primitive coin p. So here I set p to be 3/4, and coin p basically is a primitive in the language that returns 1 with probability p and 0 with probability 1 minus p. I read from the reference, and then I store the value that I sampled back to the reference, and I do that procedure twice. And by the end, when I read the reference, that represents the number of internship offers I actually get. And so the assertion at the end will fail if both coins return 0 in the case and that's the case where the reference will be storing 0. So I might ask, for this program, what is the probability that this program crashes with probability at most 1/16? And that only happens when the assertion actually fails. To show this claim, we can use a logic that was presented at last year's ICFP called ARIS. And ARIS is a high-order separation logic for reasoning about error bounds of sequential probabilistic programs. And the key idea of ARIS is that we internalize probabilistic error as a separation logic resource, which we call error credit. And an error credit is written in this form. And this assertion, this epsilon is a real number that ranges from 0 to 1. And if you own this kind of assertion, owning epsilon error credit, intuitively, you're trying to prove that the goal is true with an error of at most epsilon. And you can see this intuition a bit more precisely from the adequacy theorem of ARIS, where if you're able to prove the Hall triple on the left with epsilon error credit to start with in the precondition, then when you run the program, the probability that you get a value from the program that is not in the postcondition, or what we consider an error result, is upper bounded by epsilon. There are only 3 rules you need to know to use error credit properly. You can split error credit by summing them. If you have 1 error credit to start with, you can prove any postcondition. And this is somewhat intuitive because from the adequacy theorem, if you own 1 error credit, you're trying to prove that the mass of some distribution is upper bounded by 1, which is true for any probability distribution. But the most interesting rule for error credit is what happens when it interacts with the random sampling operation, in particular when we perform a biased coin flip. If we have epsilon error credit to start with, you can choose any epsilon 1 and epsilon 0 such that its expected mean is smaller or equals to epsilon. Then whatever value n you get from this coin flip will get exactly epsilon n error credit. And this is nicely illustrated by the diagram on the right. It's also somewhat important to emphasize that this is a separation logic. So there might be more resources around the precondition and postcondition that might be framed out using the normal frame rule in separation logic. So with error credits, let's see how we can use these rules to prove our claim that the program actually the probability that the program crashes is at most 1/16. And to do so, we can apply adequacy, and it suffices to prove the Hall triple on the left. And the postcondition is true here because the only time the whole thing runs is if the assertion goes through. So now with the Hall triple on the left, let us symbolically step through the proof, allocating the reference, coming to the first coin flip. Here, with 1/16 error credit, we choose to supply 0 error credit if we sample 1, and 1/4 error credit if we sample a 0. It's somewhat interesting to emphasize that we're able to amplify error credit for some particular branches, and this is going to be useful at the end of the proof. We perform a case split on the value of x, and the interesting case is when x is equals to 0. So let's continue with that. So we have 1/4 error credit. We continue stepping through the proof, coming to the second coin flip. And here, we apply the same rule again, where we split error credits, but in a slightly different way, where we supply 0 error credits if we sample 1, and 1 error credit if we do sample 0. Again, as before, we apply case splits on the value of x. And if we do sample 0 here, we actually have 1 error credit, and we can prove any postcondition. So that case is solved. For any of the other cases, if we do continue step through the proof, for example, in the previous case where we do sample 1, at the end, the reference will be storing a positive number, and the assertion will go through, and that concludes the proof. So that's all nice. With errors, we can now reason about error bounds of sequential probabilistic programs. But that's not the end of the story, because this is a session on concurrency, and nobody in their right minds apply for internships sequentially. So let's rewrite a program to use a bit of concurrency, where now we use the parallel composition operator to split the interesting component. And we also modify the program a little bit to use the fetch and atomic add instruction that reads from the reference and increments the reference with a value x in 1 atomic step. Now, looking at this program, the behavior of this program is pretty much the same as before. And so we might want to prove the same error bound. But we can't do it with errors, because now we're in a concurrent language. And so we need something stronger. And here we introduce Coneris, which is a concurrent separation logic that inherits the ideas of error credit for reasoning about error bounds of concurrent probabilistic programs. And the good news is that all the rules from errors for error credit reasoning and the standard rules from normal concurrent separation logic are exactly the same in our logic. And it should be mentioned that although this is quite nice, this does not fall through directly. The model of Coneris is somewhat different from all the other previous logic, and we have to prove these rules from scratch one at a time. As mentioned, now we're in a concurrent language. We have to extend the operational semantics to reason about a concurrent thread pool, and we decide which thread to step through a scheduler. And so the adequacy theorem is modified to quantify over all possible schedulers, which might be stateful and probabilistic. So now with this Coneris, let's try to use Coneris to reason about our concurrent probabilistic program. Again, we apply adequacy. So it suffices to prove the similar-looking Hall triple on the left. We step through the proof symbolically, coming to the interesting part of the program, the parallel composition operator. And we might just want to apply the normal rule for parallel composition. But there are two issues. Firstly, we need to know how we can share the reference resource, because both threads will modify and read the reference. But also, we don't really know how we're going to split the error credits, because if we split it naively into a half and supply 1/32 for each branch, or each thread, that is not enough for any of the thread to actually avoid sampling 0. And the key idea is to use invariance, which is a logical facility from concurrent separation logics that allow us to share resources between threads. And we support the familiar-looking rule from many concurrent separation logics, where if the expression is atomic, meaning that the expression will step to a value in one single step, we can open the invariant and temporarily access the resource in it from the precondition, and we just have to reestablish the invariance at the end of the atomic step. And again, even though this is the standard rule from concurrent separation logic, we still have to prove this again from scratch because the model of Coneris is very different from other models. And the key idea now is that now we have invariance, we will store both the error credits and the reference resource in an invariant to describe how it changes. And here is a very high-level intuition of what the invariant looks like. And intuitively, the invariant encodes a state transition system. It stores three things. It stores the error credit, it stores the reference resource, and it also describes how the value of the value stored in the reference and the error credit changes with what the thread sampled. And these arrows represent the value that is sampled by the coin flips, regardless of which one goes first. So for example, in the case where both coins do sample 0, it goes all the way to the state where we have one error credit, and then that allows us to prove any postcondition. So with all the power of invariance from concurrent separation logic, Coneris allows us to reason about error bounds of now concurrent probabilistic programs. But in real life, when we verify programs, a lot of the times, the software is pretty big, and it's very hard to verify everything in one single pass. What we want is that we want to be able to prove specifications in a modular way. Let me be a bit more specific with this example, as an example. Here we have, this is the concurrent program we saw before, and we can split it into two halves, a module side and a client side. On the module side, we implement a concurrent randomized counter module that exposes three functions. You can create the counter, you can read from the counter, and you can increment the counter with a number based on the number of a biased coin flip. And now the client is modified to use the API provided by this module. Now the question is, can we provide a nice specification for the module that allows us to reason about the error bound of the client without having to know how the module is implemented? And this is a relatively tricky question. And the main problem with this kind of modularity is boiled down to how we interact with invariants. Previously, when we are reasoning about the client code, we have to access resources in the invariants. We have to do it once for the biased coin flip when we modify the error credits while going through the state transitions system. And we also have to do it another time for the fetch and atomic add instruction where we might need to modify the reference resource. But the only rule I just told you that allows you to modify and access resource in the invariant is this rule, where we have to know that the expression is atomic. But now we're trying to hide the implementation. And so the specification of the module should be somewhat expressive enough to enable us to actually access resources in the invariants. And in this particular case, we have to do it twice. To solve this problem, we can take a step back and ask ourselves, how do we traditionally prove the correctness of concurrent data structures? And a standard notion of correctness for concurrent data structure is the notion of linearizability, which intuitively is the idea that all the interesting operations appear to take place at one single atomic step, which we call a linearization point. In concurrent separation logic, we try to capture this notion of linearizability through logical atomicity. And it allows us to reason as if the data structure has that modifies the interesting state in one single point in time. And in iris logics, like Iris logics, this kind of notion is captured through something called whole cap specifications. The key idea of whole cap specifications is that we parameterize preconditions with these view shifts written with this fancy update modality. And these fancy updates are also the logical facility that enables us to open invariants very flexibly. However, this is still not enough for our problem, especially when we have error credits and probability in the mixture as well. To explain why this is not enough, consider different implementations of the randomized counter module. This is the implementation you saw before for incrementing the counter, where we throw a biased coin flip to perform the sampling. But we can also do something a bit more strange, where we, instead of throwing a biased coin flip of 3/4, we can just simulate that with a fair coin, and we toss it twice. And we only sample 1 if both coin flips actually get a 1. I can also do something a bit more funky, where I implement the interesting random sampling with a rejection sampler, where I keep on generating a 3-bit number until I get something from below 4, and depending on the value between 0 to 3, I decide whether to sample 1 or 0. And the key idea is that even though all 3 implementations behave the same, the randomness operations do not happen in one single step. In other words, they're not atomic. But from the outside observer, they are logically atomic. And this is very strange, because for these operations, the number of times you might modify error credits is not like the modification of error credits might happen over multiple steps. But we want to reason about them as if we're all able to modify error credits in one single linearization point. And it's a bit challenging to figure out how we can condense the randomness into one single point in time and provide a specification that is satisfied by all 3 implementations. And the key idea is that we need to capture something called randomized logical atomicity, which intuitively describes how modules can commit to some future probabilistic choice in a logically atomic manner. And in Coneris specifically, we captured this notion through a probabilistic update modality, which is somewhat similar to the fancy updates you saw before, but it also allows you to update error credits. To demonstrate that this approach is very flexible, we provided a lot of case studies, including this one, where we implemented a thread-safe idealized hash function. We modeled the hash function as a random oracle, meaning every time we hash a key we haven't hashed before, we choose a random number to be the final hash. And it's also thread-safe in the sense that if it's shared by concurrent threads and both threads hash the same key, they should be mapping to the same value at the end. We provide a flexible specification where if you initialize the hash, you will get a hash key abstract predicate for every key in the domain of the hash. And this hash key predicate represents the knowledge inside the hash. It represents what kind of keys, what kind of values are mapped to from each key. And initially, all of these hash keys are uninitialized because we don't have no knowledge of what each key will map to. And you can pre-sample and decide which key it will sample to through a probabilistic update modality. And we have a very flexible way of also splitting error credit depending on the value a particular key is mapped to. Finally, if we do have the knowledge that a particular key is hashed to some value v, and when we do run the program where we apply the hash function on the key, we'll get that particular value back. To show that this specification is expressive and useful, we implemented a concurrent Bloom filter using this specification. And we're also able to prove tight bounds on the probability of getting a false positive. And it should be mentioned that, to the best of our knowledge, this is a new result because the the proof of this requires the reasoning about the intersection of probability, concurrency, and local state. In conclusion, Coneris is a separation logic that enables us to reason about error bounds of concurrent probabilistic programs by inheriting the rules of error credits and rules for reasoning about concurrency from concurrent separation logics. In addition, we can do so in a modular way by capturing randomized logical atomicity with the probabilistic update modality. There are more things in the paper. For example, details of the specifications and the proofs all presented in this talk. And also, there are also more convincing examples. For example, a lazy sampler and a concurrent amortized collision-free hash, which is inspired by a similar example from the original Aarhus paper. I thank you all, and I welcome any questions. If you do have any research internship opportunity and you find this kind of research very interesting, I'll be here for the next few days, so do look for me. And my advisor, Lars, is also recruiting any interns, PhD students, and postdocs. If this research seems very interesting to you, I'm happy to chat with you about my experiences in Aarhus. With that, thank you all.
How hard is it actually to find those proofs? Like now you have the formalism. How hard is it to actually prove anything?
A lot of the rules, so for example, the one where I showed you where you have the concurrent probabilistic program where, like the new modification, like this one, like even though the invariant looks, the invariant matches a lot of the other proofs in just normal concurrent separation logic. So the way we encode this invariant is just very standard, using ghost resources and just normal, it's kind of somewhat intuitive as previous concurrent separation logics that don't have probability. So we argue that it's actually not too bad, and it's, if you understand normal separation logic, this one goes through pretty nicely. My intuition, so I think I don't really agree with the notion that the error credit is always decreasing, because although it is the case that you can spend error credits as you go through, with the sampling rule, you can actually amplify the error credits for some particular branches. So in that case, I think the idea of monotonicity is not exactly the same as what's in how we use error credits. Yes.
Thank you very much. Well, thank you.